Okay, moving on to carbonyl compounds, question 7. Okay, question 7 is a 2017 A-level question. So we have cinnamon aldehyde, which is the compound mentioned over here. So you can see that in this compound, this cinnamon aldehyde exists in the trans configuration. Okay, so E and F have the same molecular formula, but show different type of isomerism. Each isomer contains a benzene ring, and both reacts with 2,4-DNPH. So again, 2,4-DNPH, recall what is it used to test for? It's to test for your aldehydes as well as your ketones. Okay, so in this case, you're supposed to propose two isomers E and F, which are isomers to that of cinnamon aldehyde, and they must be aldehyde and ketone and contain a benzene ring. So quite obvious, cinnamon aldehyde is a trans isomer. The first isomer we can draw is to draw the cis isomer. So you can see the two hydrogens here are on the same side of the double bond. So the type of isomeric relationship, it's your cis trans isomerism. Okay, so take note of how we draw skeletal, how we use skeletal formula to draw your cis trans isomerism. This is the, in this case, this is the trans way of, so this is the cis way of drawing, and in this case, right, trans, right, because you can see they are on opposite end. Okay, now for the other isomer, it must be a constitutional isomer. Okay, why? Because if you look at all the carbons in cinnamon aldehyde, all the carbons here are all sp2, and as a result, it's not possible for enantiomerism to occur. Okay, so recall there are only three types of isomerism that you have learned. Number one, constitutional, which means you have the same molecular formula but different structural formula. So you have different types of bonding. The second one, it's your cis trans isomerism. Typically occurs with a CC double bond, because CC double bond has restricted rotation, and you must have two different substituents on each carbon of the CC double bond. Alright, that's for cis trans isomerism. And the last one is where you have enantiomerism, where you must have a chiral carbon. A chiral carbon is a sp3 carbon with 4 different substituents on it. Alright, and there's no internal plane of symmetry. So in this case, as I mentioned, cinnamon aldehyde, there is not possible to have any enantiomerism. So the only way you can think of is to have a constitutional isomers. Alright, so one easy way, instead of an aldehyde that you see over here, I can convert it to a ketone. So I shift the position of the double bond O to somewhere in between, so that I can get a ketone, which also gives a positive 2,4-DNPH test, an orange PPT. Alright, but it's an isomer of that of the aldehyde. Okay, so in this case, the type of isomerism will be constitutional isomerism. Now, there are many other possible constitutional isomers, so over here I've given you a sum of them. So, importantly for you to take note, you have to propose an isomer which contains an aldehyde or a ketone. Alright, and either an aldehyde or a ketone in order for isomer F to be applicable, because it must contain a benzene ring and must react with 2,4-DNPH. Okay, when you are proposing isomers, please always also counter check the structural formula against the molecular formula. They must have the same molecular formula as cinnamon aldehyde. Okay, so they must have the same molecular formula as cinnamon aldehyde. So if you check the molecular formula of cinnamon aldehyde, you have in total 1, 2, 2, 3, C9, 5 plus 3, H8, and then O. Alright, so you must have this molecular formula C9H8O when you're proposing isomers. Okay, with that, let's move on to the second part. The second part basically shows a reaction scheme in which cinnamon aldehyde, then you can see that the alkene remains, right? The alkene pretty much remains unchanged. But what happens to the aldehyde? The aldehyde has been converted to a hydroxynitrile, right? Hydroxynitrile. Okay, so you have added in essentially a H and a CN across the CO double bond. So this is basically nothing foreign. This is a nucleophilic addition reaction. The type of reagents and conditions required will therefore be your HCN with trace amount of either NaOH and Na or NaCN as catalyst, and cold temperature to prevent the HCN from boiling off. Okay, because HCN is toxic. So this is the standard bookwork reagents and conditions for your nucleophilic addition of HCN across the CO double bond. Now, then if not, then we take a look at the subsequent reactions. For G, it can be reduced by both hydrogen or lithium aluminum hydride. So in this case, remember, hydrogen and nickel, what can it reduce? Alright, so in this case, It's a reduction reaction. Hydrogen and nickel. Let's take a look at the functional groups then. We have our alkenes, we have our nitrile, and we have our secondary alcohol. Okay, so in this case, can hydrogen, nickel reduce alkene? Yes, it will become it will reduce the alkene to alkane. The hydrogen nickel can also reduce your nitrile. Okay, so for compound H, basically your CN, right, will become CH2 NH2. Okay, so you add hydrogens across CN. Okay, so then of course the alkene will become an alkane. Okay, so reduction of both your alkenes and your nitriles. Okay, so nitriles reduce over here, alkene also reduce over here. Alright, now take a look. They mentioned the compound H has a molecular formula of 165. So you can double check if you want to, but really it's not quite required, given that if you understand your chemistry well, you know that this is likely to change. Now, then they give you a molecular formula of 163 to highlight to you the difference between lithium aluminum hydride and hydrogen. So if you recall, lithium aluminum hydride can only reduce, it cannot reduce alkene. Alright, it can only reduce the nitrile. Okay, so your nitrile in this case is reduced to CH2NH2. Okay, so reduction of your nitrile only. Okay, so you can see you have a CH2 followed by a NH2. So this part here is a CH2 and NH2. Alright, so if we use scatter formula, the carbon is shown as a kink. Okay, so the main difference, why is there a difference of MR of 2, is because of these additional two hydrogens across the CC double bond, alright, which is being reduced. So you added one more hydrogen across, and that corresponds to the MR of 2. Okay, now let's take a look at the isomer 1. Isomer I, which is this compound here, it's formed because lithium aluminum hydride can only selectively reduce. So this looks like a very difficult question to answer, but in other words, the question is just basically asking, why can't lithium aluminum hydride reduce alkenes? Right, and this is not covered in your lecture so far. So I will suggest you guys to copy this answer into your lecture book under the topic of carboxylic acid, RCOH. There's a summary table on page 16 of all the reducing agents. Right, so you can copy this. Why can't lithium aluminum hydride reduce alkenes? So this is something that you need to know. Alright, for hydrides, okay, hydrides in general, HYDRIDE, hydrides is basically your H minus. Now, how do we form H minus? H minus is formed when a hydrogen atom, alright, hydrogen atom gains an electron. Okay, so you form a hydride. So when you look at hydride itself, lithium aluminum hydride, sodium boron hydride, they basically produce this species called H minus. They are sources of H minus. Now, when you look at H minus itself, what do you think? What's the role of it in an organic chem reaction? Alright, it has a lone pair, it's slightly electron rich because of the negative charge. So therefore, in this case, we can see hydride is going to behave likely as a nucleophile. Alright, because it's electron rich. Okay, so in this case, when we look at hydride being a nucleophile, therefore, we should be able to reduce, if you see, if you recall your chemistry on the RNCs, your ketones, your aldehydes, your nitriles. Right, these are some examples. Okay, why are they able to reduce your ketones, aldehydes, and nitriles? Because when you look closely at the carbon is actually electron deficient. As a result, there's a high likelihood that the hydride can be attracted to the electron deficient carbon. So if you have revised your carboxylic acid, you also know that lithium aluminum hydride, it's also the only reducing agent that can reduce your carboxylic acid. Alright. So again, all of this because of the polar CO or CN bond. It attracts the electron-rich nucleophile because of the electron-deficient carbon. Okay, the delta plus carbon, alright, which is electron deficient. So things that contain C double bond O, C triple bond N, alright, you have electron deficient carbon. So as a result, you have a hydride, alright, which can therefore attack. But compare that with your alkenes. Alkenes, on the other hand, is just a CC double bond. There is no delta plus or nor delta minus on the CC double bond, and therefore it cannot attract your hydride to come and attack. Okay, so the H minus nucleophile will not be attracted to them. In addition, we also know that the CC double bond, because of the pi electron clouds, they are electron rich. So your alkenes are functioning as your nucleophile. A nucleophile cannot react with a nucleophile. Alright? Okay, so you may want to, as I mentioned, this is something new which did not cover in lecture. You may want to copy this on page 16 of the lecture notes. Okay, if not, I'm going to move on. Okay, then we move on to C, in which we have cinnamon aldehyde reacting with aqueous sodium boron hydride to form J. So we know that sodium boron hydride is a specific reducing agent to reduce your aldehydes and ketones. Alright, so aldehydes and ketones. So in this case, the functional groups over here in cinnamon aldehyde, we have an alkene and we have an aldehyde. So quite obvious, your aldehyde, what will it be reduced to? It will be reduced to a primary alcohol. Okay, so primary alcohol is CH2OH. So take note of how we draw. So you can see the primary alcohol is reduced. You have CH2OH. Alright, a primary alcohol over here. Okay, so this is the table that you will find on page 16 of the lecture notes. You realize that lithium aluminum hydride can reduce every single functional group except alkene. Okay, so this can be found on page 16 of the carboxylic acid. I repeat again, carboxylic acid lecture notes. Alright, you may want to copy down this reasoning, alright, in B part 3 into page 16 of the lecture notes. Okay, moving on, I'm going to go through the last part, which is the mechanism. So the reaction between cinnamon aldehyde and aqueous sodium boron hydride is a nucleophilic addition reaction. So they give you some context. Alright, it's a nucleophilic addition reaction. Let's also draw the mechanism, given that hydride is the reaction species. Now some of you may be very confused. Sure, isn't sodium boron hydride supposed to be used in ethanol? Alright, that's what we have mentioned in lecture notes. So if you look at our lecture notes mention that it's sodium boron hydride and ethanol. Right? Why in this case we use aqueous. Alright, so again, depending on the context of question, you just answer accordingly. Right? You should expect the sodium boron hydride to also reduce the cinnamon aldehyde to a primary alcohol. So to draw the mechanism, okay, so we can start with naming the mechanism, nucleophilic addition reaction. So in the nucleophilic addition reaction, you of course have your cinnamon aldehyde first. In this case, what is nucleophile? Nucleophile is your H minus. H minus will attack the electron deficient carbon. Okay, so take note, arrow starts from the lone pair of the hydride, point to the delta plus carbon. This indicates a bond forming process, lone pair on H atom to the delta plus carbon atom. And then, because you form a CH bond, right? So in this case, you form a CH bond. This carbon will now have 5 bonds. The only way for carbons to remain 4 bonds is to break one of the double bond, which is the pi bond. So to show a bond breaking process, what do? We show from the bond to the O atom, which means these 2 electrons in the bond are both going to the O atom. And that's how we can get an O minus. Okay, that's how we get an O minus. Okay? With a lone pair over there. And of course, this is a slow step. Okay, because you're forming an intermediate, and typically intermediates are higher in energy than reactant, and therefore the first step is expected to have a higher EA. So once you have the once you have the intermediate, the question is how then do we form the alcohol? To get the alcohol, basically I need a H plus. I repeat again, H plus to protonate this to get an OH. So where can we get H plus from? So if you take a look at the question, where can we get H plus from? So at cinnamon aldehyde and sodium boron hydride, we did not add any acid. So the only possible place we can get H plus will be from the aqueous medium. So recall, what's your aqueous medium? The aqueous medium in this case is your water. Okay, it's your water. So in this case, I need to therefore provide water to contribute the H+. So let's take a look at the arrow. We have an intermediate over here, right, with a lone pair. So water needs to contribute the H+. So we draw in the water molecule first. Okay, of course we know that the H of the water is delta plus. Okay, so as a result, if I want to get a proton H+, the OH bond must break in a way that both electrons go to the O. Alright, so you can see arrow pushing in terms from the lone pair to the delta plus H. So I'm forming an OH bond forming. Alright, again, this H can only form one bond. As a result, the OH bond in the water molecule must break, and that's why you start the arrow from the OH bond and you point to the O. Alright, OH bond to the O. Okay, and again, why do we need to include dipoles over here? We need to include dipoles to indicate where is the electrophile. The nucleophile is quite obvious because of the lone pair. Then we need to indicate where the electrophile is, which is indicated usually with a delta plus. And once you have that, we form our product, which is the primary alcohol. And take note, what does it become? O gaining an electron will become a negatively charged, and therefore you get OH minus as a byproduct. Okay, so that's a mechanism question. Then we move on to part 3, suggest why lithium aluminum hydride is a stronger reducing agent than sodium boron hydride. In this case, basically, we know that lithium aluminum hydride, it's a better H minus source. That's what it means. Okay, a stronger reducing agent means that because we look at reduction as the case as providing H minus. So in other words, why is lithium aluminum hydride a better source of H minus? So first of all, we can consider something very simple, which is that the lithium aluminum hydride, the ALH bond, is weaker compared to the BH bond. And therefore, it's easier to break the bond to provide the H minus nucleophile. Okay. Alternatively, we can also consider in terms of electronegativity. Now, aluminum and boron are in the same group. In fact, this is their relative position in the periodic table. So down the group, we know that electronegativity decreases. Which means Al is less electronegative than boron. If I'm saying that Al is less electronegative than boron, I can also say that Al is therefore more electropositive. That means it does not like electrons. Okay, it does not like electrons. Which means if I consider ALH bond and BH bond, alright, H in the case of lithium aluminum hydride will be more electron rich. Why? Because there is a bigger difference between the electronegativity. Right? H can Al doesn't like electrons, so Al will lose its electrons more readily to H. You have a more polar bond over here. Alright, and as a result, it's easier to form H minus because the electrons are shared unevenly. More unevenly in Al and H compared to B and H. Alright, so you can see that the H in aluminum hydride is more electron rich, therefore more easily form H minus. Alright, because you need to get more electrons to in order to form H minus. Alright, and with that, that concludes the discussion for question